we've got our upper half plane, and there's an action on the upper half plane by the group gamma naught n. And what this means is that we can consider the quotient gamma naught n, if it acts on the half plane mod gamma naught n. What this quotient is saying that it's the set z in the upper half plane modulo the relation z is related to w if and only if there exists a gamma in gamma naught n such that z is equal to gamma w. And just written like this, you might wonder what this looks like, and that's important, right? The geometry of this space is going to be relevant for a lot of calculations. So a fundamental domain for this quotient, upper half plane mod gamma naught n, is a set if it's a subset of the complex numbers, or maybe of the upper half plane, such that if z is equal to gamma w for some gamma in gamma naught n, and both z and w are in the fundamental domain, then necessarily gamma is the identity matrix. So that means that essentially if z and w are equivalent under the action of gamma naught n, then only one of them is in the fundamental domain, or said otherwise, you're taking one representative from each gamma naught n orbit and putting that in your fundamental domain. And then the second condition, so this is condition 1, and condition 2 is that every orbit has at least one representative in, I think actually here you're supposed to take the closure of F in the usual topology in C, but it's not super important. And of course, because of condition 1, really we're saying that it has exactly one representative. So that means that if you just take any point in the upper half plane and you look at its orbit under gamma naught n, it has to intersect F at some point. It has to intersect F in exactly one point. And this is, there are a lot of choices for a fundamental domain, and you can pick some weird ones. So there's a standard choice for that people make for SL2Z, and that is you take, so this is the line, this is the unit circle, And then here you take these vertical lines. So this is x equals 1/2, and this is x equals minus 1/2. And then your fundamental domain is this area going off to infinity. This is the fundamental domain for SL2Z, which is also gamma naught 1. And this is the simplest fundamental domain, essentially. After that, things can get more complicated. Let me give an example, and the reference that I'm going to give for this is this paper of Zagier from 1985 called Modular Parametrizations, something. I forget the the full name. This is enough to find it. And if you take n to be prime, then one fundamental domain you can choose is you have all these little semicircles, and then you go down to 0, and you have the same number of semicircles on the other side. This is okay. And then you have this this thing, and your fundamental domain is this stuff up here. And the number of so these are really copies of the fundamental domain for SL2Z, but just distorted. So all of these, in here, like this, all of these are copies of what we had above, but a little bit smushed. Right? All these are this. And then this one down here is a copy of this under z maps to -1 over z. So it's just a flipped version of it. And sometimes it's useful to have a specific representation for to work with. And so this works when n is prime. This is figure 2 in the paper if you want to check it out and get more details on exactly what this fundamental domain is. And you'll notice that there's a cusp here. So let's talk about cusps. Really, there are two cusps up here. There are cusps at I infinity and 0. Right, so this is the cusp at 0. So it's always the case that when you're working in prime level, you're going to have two cusps. And in general, you can have more cusps. So let me see. Here's a full classification of cusps. So the set of cusps or representatives for cusps is, of course, you can take different fundamental domains, and then your cusps will look like they're in different places. But you can just take, a representative set of inequivalent cusps. So a representative set of inequivalent cusps are given by real numbers or rational numbers u over w, such that w divides the level. U and w are coprime, so this means GCD UW equals 1. This is a shorthand that I'll use often. And these range over U mod the GCD of W and N over W. So and the reference for this is this textbook by Goldfeld and Hundley. And this is proposition 3.3.8. So, for example, if n is prime, then, W divides n implies W is equal to 1 or n. And then we're ranging over, and W GCD with n over W. When W is 1, this is the GCD of 1 and n, which is 1. And when W is n, this is the GCD of n and 1. So this is always ranging over U mod 1. So this is going to give that this set just has one element in it. Right? So this is going to be just the set, or it's both of there are going to be two elements in the set, right? There's going to be, say, 1 over n when W is n, and 1 over 1 when W is 1. Now, up here, we had two cusps, 0 and I infinity. So what's going on? Why do we have 1 over n and 1 here? It turns out that 1 over 1 is equivalent to 0, the cusp 0, and the cusp 1 over n ends up being equivalent to I infinity. And here what equivalence means is is explained here. Maybe when it comes up later we can talk about it then, but it's not so important for now. So being able to list all the cusps, catalog them, and do whatever calculations need to be done at each individual cusp, that's something that we're going to have to do later when we're doing some interesting stuff. So it's good to know about this geometry.